Good morning, everyone. Hello, and thank you for joining us today. My name is Chris Padilla, and I work for the Transportation Learning Network. Today's presentation is brought to you by the Transportation Learning Network. TLN is a program of the Upper Great Plains Transportation Institute at North Dakota State University and is a partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, and the Mountain Plains Consortium, which includes 8 universities in Colorado, North Dakota, South Dakota, Utah, and Wyoming. Our presentation today is an MPC research topic. The MPC report is MPC 17-319, and it is about cracking and debonding of a thin fiber reinforced concrete overlay. Fiber reinforced concrete has been used in bonded resurfacing overlays and assumed to have improved performance as well as cost effective. The benefit of improved toughness by incorporating fibers has proven to reduce cracking, yet other deformation characteristics and the bond interaction to the underlying layer is unknown. The following objectives of this study include: investigate the impact of incorporating fibers on the mechanical properties of the bond by means of a wedge splitting test and the shear bonding test, investigate and characterize the effects of fiber on debonding behavior with experimental tests, and develop a finite element model which predicts effects of debonding through shear or liftoff. Our speaker today is Dr. Amanda Bordelon. She is an assistant professor at, this actually just changed. She recently moved to Utah Valley University. She received her BS, MS, and PhD degrees in civil and environmental engineering from the University of Illinois at Urbana, Illinois in 2005, 7, and 11, respectively. She's actively involved in professional societies and committees including the American Concrete Institute, Transportation Research Board, and the International Society for Concrete Pavements. Her main area of expertise is in the fiber reinforced concrete pavements. Research topics include fiber reinforced concrete, concrete pavement design, ultra-thin white topping, concrete overlay bonded to asphalt, fracture mechanics, and X-ray CT imaging. She told me that she was working this weekend with the concrete canoe team at the Utah Valley University, and actually sent me an email at 2 o'clock in the morning, and I asked her if she got any sleep at all last night, and she said she's feeling a little under the weather, so she may be taking a couple little breaks throughout today's presentation to take a drink of water. So she just stand by if she happens to pause for a little bit.
So yeah, I'd like to reiterate thanks for everyone who suggested having this as a topic, and I want to also thank the other people that were involved in this research project. As you mentioned, this is a topic talking about cracking and debonding of a fiber reinforced concrete overlay. I've been doing fiber reinforced concrete for many years now, and this one's near and dear to my heart because it's related to one of the main issues in pavement design that we're still struggling with in terms of incorporating fiber reinforced concrete. It was a project funded through the Mountain Plains Consortium, and I guess that's Region 8. And then it had some matching funds also coming from Utah Department of Transportation and the University of Utah's startup funds. I was actually the principal investigator on this project, and then I had a doctorate student, Thomas is his name, who's now in Korea. And a lot of the testing was done at University of Utah's campus. So a little bit of background for you in case you haven't done much fibers. Fiber reinforced concrete has been done for many years. I would say it's most commonly been used lately since the 1990s. There's a lot of overlays that have been cast and a lot of projects that are available for people to drive on these days. And there's even a database that you can go look up where they're located if you're ever curious about that. For the background on it, fiber reinforced concrete has been very well documented to reduce crack widths, and at least in lab specimens. And then it's also reducing crack growth or propagation. It's also delaying that as a result of it. And there's even slab testing that has been performed full scale that has verified that it increases the load carrying capacity of the entire slab. So there's a benefit to using this in pavements because a lot of times we're designing them to be either thinner or larger joint sizes as a result of these benefits. There's still some common questions that I always hear almost all the time when I talk about it to people, and that is most people want to know how many fibers do you actually put into the mix. As a little plug to myself, I'm involved in a software that is coming out in January to help you figure out what your residual strength ratio value needs to be, or residual strength stress value will be, in order to get the performance you want. So I guess look for that if you're curious for that. That's coming through the National Concrete Consortium. But that uses a ASTM test standard, which you can see down here on the right. It's a 6-inch beam that is same as your standard flexural strength. You just need a yoke to measure the deflection here over a larger post-cracking deflection. And that stress value that you get after it's cracked is actually measuring the benefit of how the fibers engage and carry the stresses after it's been cracked and opened. And that can be used directly into pavement design and can predict the increase that you see in load carrying capacity. So we usually figure out how many fibers it takes then to see by doing trial and error batches. Since there's a lot of different fibers out there, there are suggested values based on experience, but essentially that is the test standard to figure out how it's going to benefit the pavement. One of the other challenges that I have come across is most people don't actually know, and this is researchers as well as industry, on how much it actually changes the crack width or the joint spacing that is needed in order to see that benefit of fibers, like how much narrower, how longer of a joint size can I actually get, and then even questions about the bond. A lot of these thin overlays are assumed to be bonded to the previous layer, which is often constructed on asphalt, but it can be on concrete as well. And that bond is assumed to be there for its lifetime, but it's not always guaranteed. So that's one that we thought we'd address with this research here. So a little bit of basics here. We have a plain pavement here at the top. This is one showing as it's been constructed. As time goes on, that pavement will curl when the temperature changes. So if it gets warm in the day, it will curl up a little bit. This is exaggerated from real life, but essentially it's warming, so the surface gets larger at the top, and it might open on the bottom if it gets beyond the tensile strength of the material. And at night we get often cooling, so it's cooler on the top and it stays warmer on the bottom, and we might see a crack at the top. This is considered often the design worst case scenario, although you can get bottom up cracking. We are primarily looking at top down cracking, which is here in the nighttime. And then you also get this debonding effect that can occur because as it opens and stretches at nighttime, it could also lift off and create this delamination down here at the underlying layer. So I guess one of these things I thought I'd mention is, why are these a problem? Essentially, if you have wide cracks over time, because you have cycles of these, so they end up stretching further and further over time, we can get more moisture and other things to fall into the joint, and that can cause it to crack further and deteriorate faster. And we also have a reduced load transfer efficiency. If the crack is too wide, you don't get that aggregate interlock, and especially with the fibers can't transfer the load either if it gets too wide. The debonding aspect of this, if we have the higher, if it does separate completely from the underlying layer, then all of the tensile stress of that material has to be within the thickness of the pavement. And a lot of times the concrete is originally, because it's designed to be bonded to the underlying layer, it requires the tensile stresses to go in the underlying layer. And by debonding, now we see the tensile stresses in the concrete, which causes it to sometimes crack from other deterioration, but it's mainly because it had debonded. Again, moisture can get into this space down here, this void, and we can get things like faulting and stuff that cause further degradation again. So the background research on this, again, the motivation is cracking and debonding we have seen can occur even with fiber reinforced concrete, although it's been said that it's reduced. So we wanted to look at that and see how much does it actually change, since it's an important pavement design consideration and maintenance aspect. There are a lot of field projects that have been, like I said, used fiber since the 90s. There's one specific one that we used here in this study because it was a nice controlled environment that we could look at specific aspects. It's been monitored over time, and that's a field project that looked at different slab sizes. So that's what I'm gonna talk about here in a little bit. And then again, one of the unknowns is how much does the crack width actually change when you have fibers or when you use these larger slabs. We do have analyses that have been done before, back in the 70s, to figure out how crack width is related to slab size, and that's actually something that we're going to piggyback on this for the research. But we wanted to look primarily at how does it change then going into the fiber reinforced concrete as the material, because that is specifically designed to go across those cracks. So we're going to see if we can predict an equation to calculate what that crack width will be. And then we also did a finite element model, and this is to investigate and predict, again, that cracking sort of in a simulated environment that matches closer to the field rather than just some equation. And we did some testing, again, to sort of measure what that bridge stress is and the bonding that actually goes at the interface. We actually did the finite element and the testing simultaneously, although I show them in this order, but that way the testing results actually were used in the finite element model, and so we could help validate those results. So a little bit about the order. Normally we show this at the beginning, I'm showing it here at the end, or as we go. We've done a little bit of background motivation. I'm going to talk about the crack width predictions, those equations that we had used, and then the finite element modeling, and I'll go into the testing that we did and the conclusions. So a little bit into, before I get into the crack width, I wanted to also introduce the field project that I was talking about. So this is a road that I've actually constructed myself. It was in Rantoul, Illinois, constructed in 2009. It has 0.5% volume fraction of a I think it's polypropylene fibers. That is a very large amount for most overlays. Most overlays tend to be around, we've seen anywhere from the 0.1% to the 0.5, so this is on the higher end. I would say most of them are probably around 0.2 or 0.3% on most of the overlay projects that you'll see, again, done in the 90s or later. This project was monitored over time for the crack width using a crack gauge, and also looking at delaminations using a chain drag system. The project unfortunately actually never saw any traffic loading, but that was also nice because it simplifies the analysis later. It's only been subjected to environmental, so temperature and humidity changes over time. So yeah, it's a much simpler because you don't have to worry about whether the crack was caused by temperature or traffic. But there are pavements that have been done with traffic and temperature. So that's a different study though. So anyway, this section though, what was unique about it is there was 3 sections and they had several slabs in each section. The sections had different joint spacing. That was the main variable here. They varied from 3.5 feet to 5.5 feet and then up to 11 feet joint spacing. And this was again just to see how sensitive fibers are. Typically right now we design fiber reinforced concrete overlays to be between 4 feet and 6 feet. And if you get to parking lots, then it's more on the 4 feet side. usually mainstream highways or parking lots, or, well, not parking lots, sorry, mainstream highway or bus pads and stuff will go more in the 6 feet realm. But this is also, because it had so much fibers in it, we thought we'd push the limit and make it actually only 2 inches thick. So it's 50 millimeters of concrete, so it's super thin. And it's on what, after it's been milled, the asphalt was also very thin. It was only 2 inches. There was underlying thick asphalt, sort of binder course below that, and then a lime modified subgrade. So it was a very stable and strong base. There wasn't any defects in the base layer. So it was assumed that it would bond pretty well and it would stay that way. So, in this study, we are looking at things again. Crack spacing is a term that I'm going to be using because most of the fiber reinforced concrete overlays that have been done, and even especially in this test section, we have noticed that there's either no mid-panel cracking or very few mid-panel cracking. So we decided to, well, ultimately we still are using crack spacing, so the space between located cracks from the top down. When there was no mid-panel cracks, it actually equaled the same as the joint spacing, or in some of these cases, not every joint actually cracked. So in those cases, the crack spacing was larger than the joint spacing, which is actually very common from a lot of observations with fiber reinforced concrete. Is we've noticed especially if you cut like a 4-foot joint or less, we tend to have not every joint crack initially. So it will appear to have a larger crack spacing initially. So as I said, this field project has been monitored over time. At as early as 3 days, we went out there and measured the cracks. As I said, not every joint cracked. So even so the 11-foot spacing, there was still some slabs that did not crack. So there was a section of 22 feet, essentially, without a crack. In the 5-foot spacing, 6-foot joint spacing, we also had large sections between cracks, or between cracked joints, which is, like I said, it's actually fairly common when you've done this a lot that you see that not every joint will crack initially. As time went on, most of these joints did eventually crack. So by 20 days, when we went back out there, we saw that it was 11-foot spacing, roughly 5.5 or 6-foot spacing, and 3.5 or 4-foot spacing. So, and these were essentially by 20 days, every joint finally did crack. When we look at the crack widths of those joints, initially they're pretty small actually. And then over time, they do get bigger because, as I mentioned with thermal loading, this is 20 days, but it's actually cast in the summer. And even in the summer, the joint will eventually open up just from temperature. It's not a significant amount. I mean, the 11-foot joint spacing here has less than 1 millimeter of crack width, which is considerably smaller than most unreinforced pavements. So we'll get to that in a little bit. So a little bit more, again, with what was measured, we did measure a lot of specimens. We did compressive strength and flexural strength, but we measured shrinkage as well with the free shrinkage test. It's the single, like a prism that's spun on a measuring device. We measured that from the original truckloads and they were in a controlled environment for that. And then we could get an average shrinkage property for that mix. We also had thermocouples embedded in the concrete and also, or in the pavement section, and the air quality, or air temperature. So we can measure the cycles that it went through every day from, here again it's showing from 0 to 20 days. So this is pretty early age. But you can see that at this location, this time, it went through about 17 or 18 degrees Celsius change per day. So some of the review of what this field project was telling us is we noticed that the crack width did increase as the joint space increased, which is standard for most pavement designs. So if you make them longer, they're going to have larger cracks between them. We also measured bond strength. I didn't really show that earlier, but we wanted to see how it bonded to the underlying layer. We did a pull-off torsion test. So we got some strength values, and this is pretty comparable for most overlays, other projects that have been done. So I guess essentially that means that it is bonded. The crack widths that we saw in the field, we noticed that they were a lot smaller than what has been predicted in things like the AASHTO Pavement ME. So this is where we decided to come up with an equation to see how much has it been reduced by having the fibers involved. So if you go into the AASHTO Pavement ME software, behind the scenes is an equation that was written in 1977 by Michael Darter and Ernie Barenberg. And this is an equation that calculates for the joint size, or sorry about that. For the joint size, the joint spacing L, the crack width is calculated based on a coefficient, and then the coefficient of thermal expansion and the temperature that it changes in a day, and then the shrinkage of the material. Hold on a second. Sorry about that. So the shrinkage of the material, the change in temperature, the coefficient of thermal expansion, and as I mentioned, it has a curling coefficient and all this other stuff. So when we put in the calculated, this is the dashed lines here from the AASHTO Pavement ME software of how the crack spacing or the joint spacing is related to the crack width, we actually get a prediction here. So the black line that I'm showing here with the dotted line is the calculated from the Pavement ME software. And then we find in the actual fiber reinforced concrete pavement that it's significantly lower at all the crack spacings or the joint sizes. So for these softwares, again, we're using the real shrinkage from the actual samples, the temperature that we saw in the day, and its own calculated coefficient of thermal expansion. So all of the samples, like I said, with fibers were significantly lower, and we were trying to figure out if we could predict why it is, or find an equation that could help us predict for future pavements. So there are some other researchers that have looked into this concept, especially of how fibers affect crack width. One of them was actually through Rylam, and this has, it calculates the crack width based on a coefficient, and then the crack or joint spacing, and then the reinforcement. And this is actually done for a big beam, a structural beam that has fibers involved in it, or short fibers intermixed into the structural beam. So they have, for crack spacing prediction, they have a fairly complex thing here that involves how the rebar is bonded or the steel fibers are bonded, and then how the strain is distributed and things like that. But they also have this multiplication factor on the end here, which is essentially looking at the aspect ratio. So the length of the fiber and the diameter of the fiber relative to each other, so how long or skinny it is, and they have a term here, 50. So we took this concept and we thought we'd use the same term, the 50 over LF over DF as a fiber effect and see if that could help us predict how the fibers will affect the crack spacing in a pavement. Similarly, there's another person, Lofgren, who did also a crack width prediction again for beams that had structural beams that had fibers or no fibers involved in it, and they instead incorporated a multiplication factor in here, K5, which is a ratio essentially of this residual strength ratio that we liked as well because it's very similar to what we do currently for pavement design with fibers is we use a residual strength. So we looked into that as well as a multiplication factor in our equation to see if that would help. So essentially we started with that same Darter-Barenberg equation with shrinkage, temperature, the coefficient of thermal expansion, and the crack spacing. And then we used a multiplication factor. We either called it Ka, which is that aspect ratio one, or the Kb can be used, which is the ratio of the residual over the original strength of the mix. And then we use those predictions to see how they performed. And here's some results of it. So again, this is using the same original one, which if you recall was way up here in larger crack widths. It did bring it down. If we used the Ka as the aspect ratio to fairly similar numbers as the field results in all cases. And we calculated the aspect ratio from the properties of the fiber itself. The one with the Kb term, which is the residual strength property, also brought these fairly close to the actual field results. Obviously they're a little different because there's always variability that comes into play with these kind of things, but it's a much closer prediction than what we saw with just the raw AASHTO Pavement ME software. So in general, these predictions we found were within 25% of that field fiber reinforced concrete crack width, which is pretty nice to see. And here's kind of a summary of, again, they have different Y values here. So the Darter one may be really hard to see, but this goes up to 2 millimeters is what they predicted for a 11 foot spacing or 11 foot joint size. And then the prediction models with the modified term just multiplied to it does bring the stress or the crack width significantly down to less than or close to 1 millimeter. So in general, again, these predicted models, whether you use either of them, did bring it to within, in this case, 0.19 millimeters, or like I said, 25% of the predicted crack width. And then of the two, this is a little plug here too, is I prefer myself the KB version, just because it actually accounts for more detail of the fiber. If you use you could have the same fiber or same aspect ratio and you could have very different fibers, like a steel fiber and a synthetic fiber that maybe have the same length to diameter ratio, but a steel would perform very differently than a synthetic. So this Ka one kind of doesn't account for that. So that's why I would suggest more of this residual strength, because it's a performance test that actually characterizes the fiber as a whole, not just one geometry of the fiber. So again, in the presentation, I went through the background and the crack width prediction. I'm going to go into the finite element modeling now to explain how we had simulated this. As I had mentioned, this field project had a 2-inch concrete overlay and then 2 inches of asphalt remaining. There was a base course below and a subgrade. We only modeled from the base course up. We assumed since the subgrade was stabilized and it was far enough down that we felt like that didn't need to be part of the analysis. It didn't complicate it too much. Although we still had an elastic foundation assumed from here on down, which is a spring standard with a K value of 150 that we used for that. We also did only mid-panel to mid-panel because we wanted to focus on the crack in the middle or the joint, and then we didn't seem it necessary, since it's a simple model, to go beyond that into a 3D version of this at this point in time. And then I guess I'll go some details here. So at the actual interface of the slab to slab, so the joint, we actually modeled it as a cohesive property. So what that means is the material is going to go through a standard elastic stiffness, and then at some point when it reaches a strength, it will decrease. And we used a linear model to simulate how essentially the fibers will benefit over time. If it had plain concrete, it would essentially get to the tensile strength and it would drop pretty quickly. There's not much fracture energy remaining in the material if you have no fibers. But when you do have fibers, it can separate quite a bit, so it has a larger fracture energy under the entire curve. And this fracture energy can be measured with a test, and that's one that we'll talk about in a little bit when we get to the testing. So we did measure this actual property for the material and plug it back in. So plain concrete, as I said, it does have an energy, because there is some energy it takes to get to the tensile strength. It tends to be, for this mix, we found out it was around 80 newtons per meter. If you had fibers, the field mixture, the sample done at the same time as the field, had a fracture energy of 3,600. So it's significantly larger than plain concrete. And that's because it is designed to hold the cracks together and absorb energy. And if you're curious about that this same field mix also had a residual strength ratio of about 200 psi. And as I said, it's a little bit or significantly higher than most overlays have been constructed in the past. They tend to be around 100 to 150 is pretty common. So this is a lot higher than normal overlay fibers, but also, so when we did the finite element modeling, we wanted to put in, one of the challenges, as I showed, is over time, initially the whole joint, or there was some joints that weren't cracked, and then over time they eventually did crack. We wanted to get kind of an average of what that crack spacing was. So we actually just averaged it over the 3 measurements that were taken, and used this number, the basically 1.3 meters, as the joint spacing for the first section when we modeled it, because we didn't, again, we just wanted to model one joint, not the entire pavement and how it formed cracks over time. So, and then with the same second one, we did 2.5 meters and 3.5 meters. So the loading that was done in the modeling, as I mentioned, this pavement has never seen traffic. So we wanted to model similar things going on, such as that it just had thermal loading. So we actually calculated what the thermal load would be, knowing the free shrinkage strain that we were calculating from the test method we had done. And then we assumed that there was friction at the bottom with the asphalt, because we did verify it was bonded, and we found this number from a lot of research data for what's typically used for concrete onto asphalt as the shrinkage strain in a restraint environment. And the loading was actually done as a deflection loading. So we knew that the joint would move by a certain amount, and that was calculated from like a stress analysis just to calculate what the deflection would be for this geometry of a slab. And we also assumed that the temperature would change by 2 degrees Celsius per inch. I guess I don't quite have that here, but that's what we had as the loading temperature here. So the finite element modeling, again, we're just looking at one joint here essentially, and we have the fiber layer, which is from here to here. I have it zoomed in, so you only see the fiber and the asphalt. We also simulated the joint into the finite element modeling because that is a section that is not originally having any material. So we do see as the temperature changes, we get a little stress concentration at the tip of the notch. And over time, that stress gets distributed down into the underlying layer. And it can start debonding with each cycle, although it's really small early on, and as the sort of temperature cycles continue, it fatigues it and creates up to an entire section of debonding. And again, in the field we may not have seen this much debonding, but the advantage of a finite element model is we can kind of go to the extreme case and see what it would take to fail the entire section and see what it would still do. We have all the material properties that we had measured from either our testing, as I was going to show you later, or from the original field data if we had that available. So yeah, one of the observations we did also see here was that the crack width did get significantly larger once it debonded. So once the debonding started in that base layer, the crack widths were over about 1.5 times larger, just because now they had even more movement because the slab could move up and open. So this is a result showing the field data, which is the solid lines here, and then the experimental or finite element modeling data predicting what should have happened in the field. So we see in a lot of these the finite element is pretty consistent on a lot of these and very similar to the field, with the exception of section 2. It's possible we had some other issue in the field. As I said, a lot of times there's things that random probabilities that occur that could change some of these numbers. But overall, the finite element model was also very good at predicting the crack width that occurred in the field section. And this was within 0.17, whereas just the equation we had to use where we modified Darter's equation, Darter and Barenberg's equation, that was 0.19 millimeters within the field results. So they're both very good at predicting this. With our finite element model, we wanted to see how sensitive the software was with various changes in properties. So we changed or played with the fracture energy. We wanted to see if we had put in just plain concrete into that model, what would it say about the crack width? And it's hard to see some of these numbers, but that would be this first data point. It does show it's a larger crack width, and then as we increase the fracture energy closer to what we saw in the field, we see that crack width drop. And what's unique about this is you probably only need about 1,000 newtons per meter or something before you really see that benefit of the fibers. I mean, having anything in there, any fibers will reduce it, but at that point, having any more doesn't necessarily help. So having such a high fiber content didn't really help above some minimum fiber content. So that's a useful thing for the field to know, is we don't really need to always overdose some of these fiber reinforced concrete mixes. We could probably predict how many fibers we actually need. The debonding length, this is from the joint out, the total distance, and that also reduces, so it doesn't debond as much when I have fibers in it. And then also vertical deflection, which is related to that load transfer efficiency, we do see a significant drop in when we have fibers. So that is a big benefit as well. So not only does it reduce crack widths, it actually keeps the bond with the asphalt better, and it also reduces net deflection of the pavement as it goes through the thermal loads. The tensile bond strength, this is sort of how strong the fibers are with the concrete and how much they hold it together. So as I get a little worse, the fibers slip out more or something, I have a little more crack width, and if I have a better bond, I have a little less crack width. That's pretty normal. And again, this had a very drastic effect, the bond strength, on things like vertical deflection and debonding length. So we also played with the stiffness of the concrete, so the elastic modulus. This didn't have very much of an effect. So if you made the concrete a little stiffer, we didn't really see much of a change in that. And that's also related to the strength. If you increase the strength of the mix, it didn't change the crack width, debonding length, or vertical deflection very much. Uniquely though, even though we didn't model the underlying subgrade, this did have a big drastic effect on the crack width, debonding length, and vertical deflection. So if you got a stiffer base layer, which has also been found in research, we get more cracks, or wider cracks, more debonding, and more deflection. Basically, it's too stiff to handle the movement of the pavement. And if I get really soft subgrades, I actually get less crack widths, less debonding, and less deflection because it absorbs or moves and deflects with that movement of the pavement. So I didn't put a lot of this in there because I want to save on some time here, but I want to throw a little blurb in there. If you're curious, you can look at the paper. We did kind of tinker with the idea of what if you could look at how dowels react instead of fiber reinforcement. Typically we do not do dowels in thin overlays. It's too thin to have a dowel, especially this kind of pavement where it was only 2 inches thick. There's no room for a dowel. So we don't see it in thin overlays, but because we're playing with a finite element model, we thought we'd just kind of play with that idea and see if we could design a pavement that's a little bit thicker and see how the fibers and the dowels would interact. We did see that the dowels are much better at reducing crack widths and debonding than the fibers, but that's also because they're a lot larger in diameter and longer embedment lengths. But we were able to kind of predict if you had no dowels, you'd have some cracks or a various crack width, and then as you added dowels, it would reduce it. And even if you added fibers, it reduces it a little bit. So like this dot here is if you just had fibers and no dowels, it reduces it a little bit. If you added the dowels, it comes down. And if you added dowels and fibers, it's a little bit better. But usually we don't want to do both dowels and fibers because they don't, the dowels bring it down and crack width significantly on their own. But it kind of is an interesting concept that maybe leads to future exploration on whether fibers could replace a dowel if you could put the right amount, because again it is reducing it in crack width, maybe not as effectively, but that's because they're really small and there's not that many of them. So it's only 0.5% of the volume, which is not much of that cross-sectional area. So, and again, an example of that is in this joint, there's only 10 fibers that we estimated crossing that joint, so not many. So again, from the modeling aspects, some of the predictions we did see, or the equations and modeling, is we can get it pretty close from the equation to 0.19 millimeters. From the finite element model, we're 0.17. So both of them were very close to the field data. There is this fiber multiplication term that you could theoretically either put into the software yourself, or maybe, I don't know if AASHTO will update theirs one day, but you can reduce the, or you can modify how the crack width is predicted using these modifying factors. And then another thing we learned from the modeling is you actually don't necessarily need a high fiber content, because the modeling, the sensitivity showed us that you only needed, in this case, 100 newtons per meter, but probably not 0.5% by volume of those fibers in order for it to reduce effectively the crack width. So I'm going to get into testing as we get near the end here. What we did is we wanted to test different fibers that are commonly used for pavements. We chose 3 fibers on the market, and we went with, again, a much higher fiber dosage than what is typically used in overlays. And this is because we really want to see the benefit of the fiber. So even these, like 0.4% is on the high end, but it can be done for an overlay. And when you get up to 0.8% or more, we're definitely in the realm where this is a special mix. So for these mixes, in order to keep them consistent, we also used a mortar mix that had no coarse aggregate, just because we wanted to make sure it would actually fill the molds correctly without honeycombing, and so that we could actually, again, see the benefit of the fiber itself and get the true tensile properties of the fiber on how that interacts with the underlying layer and how it interacts across a joint. So we did 2 test methods. One was they're both using a cube. It's a 6-inch cube. One was to look at just how the overlay would separate from the substrate. In this case, we used concrete for the testing because it's easier to construct. We didn't have to worry about the temperature of the test setup. And we just want to see, would the fibers increase the bond or keep that bond the same? There's no theory that says it should be increased because they aren't crossing this. This is a cold joint, a cold surface when it was constructed. There's no fibers bridging it. So there shouldn't necessarily be any benefit of the fibers, but we wanted to test it anyway because it's used in the modeling. And then we did a shear test also just to see how much these would separate, and this is more again to look at the bonding. So would they slide apart differently because there's fibers in the mix? Again, there's no theory saying it should be, but we wanted to measure it for the modeling. But we found some interesting results. So when we did the tensile bond test, this is, again, for most of the samples, we had an old concrete that's been aged 28 days. It had no fibers in it. And then we cast a new mortar mix that had either no fibers or one of these higher fiber contents into it. And we put a wedge down into it to split it and see what the actual strength is and post-cracking stress is, in case it was higher than 0. But I guess here I'm gonna go back one sec. We did cast a few that were all one material. We used the mortar mix and cast the entire sample, same geometry. These are called the monolithic samples because they were all the same material. And this is actually done to figure out that fracture energy, so how much energy it takes for the material to break apart within itself. And there's a lot of curves here. Sorry about that. But we try to color code it here. So red is no fibers. Okay, so this is a zoomed in on the left, and then a full range until all of the things broke or until we stopped testing. But let's look at the zoomed in. So when you had fibers, it goes up to some strength, and then, or sorry, no fibers, and then it'll break in half. When you have a little bit of fibers, some of these here, it will get a similar peak usually, and then there's a little bit of a residual. So this is again kind of that residual strength ratio carrying through on a tension test. And some of the fibers are really great at keeping that strength. So this is it was 10 kilonewtons in this case, or maybe around 2.3 or 2.5 kips to break a 6-inch cube. And then when it gets over here, we're getting to almost the same stress at 0.5 millimeters, or if you like inches, 0.02 inches of opening at the very top. Now these aren't pure cubes because, let me go back one again, there is 2 inches at the top that were used as a notch. So I guess it's actually a 6x4 surface area here. But yeah, and then if you kept opening it further, the plain concrete without fibers can't carry any load anymore. But the fibers actually still carry a significant amount of load for larger openings. So this is why the fibers are helping maintain a crack width, is they still carry that stress across the crack. When we look at the interface, so this is where we had a mortar mix against an old concrete. Again, red ones are the plain concrete. There's not much benefit. This one broke early. We didn't keep measuring it. But some of the lower fiber contents, we did see some energy, but even here, there's a little bit. It's probably hard to see it, but there's a little energy that's still being carried. And if you actually calculate the area under the curve, that's the fracture energy, and it is, oddly enough, it's 6 times higher. So that's really significant. Just a little bump in fibers gets, a lot more energy that it can absorb, and that's why the crack width is a lot smaller. If you look at different ones, this specific fiber did 2 times higher, and then this other one did 5 times higher. So this is again why we're seeing crack reductions. But what was interesting about these is, again, this is a mortar mix cast against a plain concrete with no fibers bridging it. So even without fibers crossing the fracture surface or crossing that crack, we are seeing a benefit, even a little bit, of having the fibers. So we looked at the samples, and you can see when it broke, it often broke either on the mortar side or the parent side. And you could see that some of the fibers, just the few that were on the surface, were enough to increase that toughness. So we actually counted the fibers and compared it to the energy, and we did verify that, yeah, just having a few fibers near the bottom surface of where it's bonded to the concrete here or asphalt in a real field, you can actually get an increased bond. So that helps with that debonding reduction as well, just because there's fibers nearby that can hold it together. When we looked at the shear, this is our setup here. We have, there's basically this whole mortar section is being pushed off or pushed down here, and then these two are here just to hold this one together and keep the balance. But we're shearing this one down, and we're measuring it as we go. So again, plain concrete is in red here, and you can see that for most of them, having the fibers increased the shear a little bit as well. Not in every case. There's a case over here that either is an outlier, or maybe because we found out this had a lot of variability in this test method. So it's possible that I don't know, this test method has, I'll show you, is a lot of issues. We did see a similar thing that when we have a little bit more fibers, this isn't, I mean, you can have up to 25, or I think one sample had 35 samples. And then you could look at the bond strength that we actually measured in the shear direction. So having the fibers again maybe increases it a little bit. And this is very dependent on the fiber type, I imagine. But we saw this test method by itself was actually very difficult to perform. Just the shearing, a lot of people in research have had a hard time measuring shear strength of materials for asphalt and for concrete. So yeah, we found the same thing. There's a lot of variability in it. So one data point is actually taken off of this. It's still in the paper, but that's the 35. It was really low. So we don't really know if there's much of a trend, but the variability, you can see the R squared here is a little bit lower because there's not a consistent result on this yet. But from the testing, again, we said the variability is kind of high on some of these test methods, so you definitely need a lot of replicates if you ever want to measure this yourself. The monolithic specimens did prove that the tensile strength goes up when the energy goes up, and that's as you have more fibers essentially in the mix, and that's actually been proven by many people before. The what was odd about it though is the specimens with the fibers do have a better bond, even in the tension, so opening of the bond layer or the overlay from the old pavement. We do see a better bond with fibers, just because a few fibers are there to kind of hold that together in case the crack goes through the mortar mix or the overlay mix. So then just in general, the conclusions from this whole study was we did verify from a field data, or comparing to the field data, that we can actually kind of predict the benefit in crack width by having fibers. And you can use, at this point, you could use either of these methods, the aspect ratio with the 50 on it, or the residual strength. I would caution again that this one with the aspect ratio might need to be tweaked if you use steel versus synthetic. So it may not be the perfect method, but this one's a little better with the residual strength because it actually characterizes the fiber a little bit better and how it performs. And they both, at least for this one case, this project, were able to predict the field very well. The finite element modeling that we did also was able to predict it, which is a good thing. So if we want to use the model for tweaking other factors, we can still do that. And then the overlay specimens that we found, again, they were cast against a old aged concrete, but even against that, we did see a slightly higher, or in some cases, significantly higher tensile strength. The strength, that bond strength is usually pretty low, but just having a little bit of fibers in one of the materials, in this case the overlay, did increase the energy a little bit because, again, sometimes that crack goes into that overlay material and goes through a fiber, and the fiber becomes engaged, and we've seen that it does slightly increase that bond. So with that, I'm 1 minute from the end here. I'd like to again remind you, I'm Amanda Bordelon at Utah Valley University here in Orem, and my colleague now, who was my student, is Minuk or Thomas Kim, who's out in South Korea. And yeah, this is our paper. You can check it out, and let me know if you got any questions. Thanks.
Awesome. Thank you, Dr. Bordelon. That was a very detailed, very informational presentation. Thank you for your time and sharing that expertise. If anybody has any questions at this point in time, please go ahead and type those into the Q&A box and we'll do our best to answer those questions. If not, you do have Dr. Bordelon's email address on your screen. So if you do have questions, you want to reach out to her directly, by all means, go ahead and do that. And I'm sure you'd be more than happy to answer or field any questions you get after the fact, right?
Yes.
Yeah, okay, cool. All right, with that, we are actually at the top of the hour and not seeing any questions come in. For more information on presentations that are coming up and information on those, go to our website at translearning.org, and there you'll find all of the upcoming presentations and information where you can register. Thank you, Amanda.
Yeah, thank you.